In this project, I built a complete end-to-end MLOps system for forecasting daily taxi demand on Google Cloud. This work is actually the continuation of my previous project, where I trained a forecasting model directly in BigQuery ML using MLOps algorithm. In that earlier project, the focus was mostly on the data science side, exploring the data, training the model, and understanding the results. I turned that model into a production-ready MLOps pipeline and API. So instead of just having a model inside BigQuery, I now have modular business logic in Python for loading data, training the model, and evaluating, reusable parameterized pipelines using Vertex AI pipeline with KFP version 2, a BigQuery ML MLOps model that is trained and evaluated automatically through the pipeline, cloud storage that stores pipelines artifacts, logs, and metadata, a Dockerized fast API service that talks to BigQuery ML and serves forecasts, and finally, a fully managed cloud-run deployment that exposes the model as a live HTTP API with a small preview. The main idea of the project is start from raw data in a BigQuery, automatically train and evaluate the model, and exposes predictions through the scalable API on Google Cloud. So that is not just a model demo anymore. It's a full MLOps flow that shows how I go from data to pipeline, model registry, Docker image, and finally, a real production-style API. Before building any pipelines or APIs, the very first thing I did was setting up a clean, isolated Python environment. In MLOps projects, dependency management is extremely important. Different tools like Kubeflow pipelines, BigQuery SDKs, Fast API, and Google Cloud libraries each require specific versions. If we install everything directly in the system Python, it becomes messy very quickly and can break other projects. This setup is specifically important when using KFP version 2 because the pipeline compilers must detect and package the correct Python functions. Before I even touched Vertex AI pipelines, I built and tested all the business logic components separately. This step is critical in any real MLOps workflow. The business logic process in this project guarantees the BigQuery project and dataset paths are correct, the SQL queries are run, permissions or ADC are correct, imports work, inputs and outputs behave as expected. Because once the logic is verified, we can wrap them into a pipeline components with confidence. Otherwise, the whole system fails on Vertex AI and debugging takes hours. After we validated all business logic, the next step was to convert those functions into full production-grade MLOps pipeline using Vertex AI pipeline KFP. This phase has one goal: turn raw Python logic into reusable pipeline components and then connect them into a complete DAG. Each stage of the ML flow needed its own independent pipeline. 1. Data loader pipeline. It reads the BigQuery source table, splits data into train and test BigQuery tables, and ensures consistent cutoff date for reproducibility. 2. Train model pipeline. Using BigQuery ML MLOps, builds and saves a time series forecasting model. 3. Evaluation pipeline. Reads the train model, calculates the AIC score, and returns a numeric output. Each pipeline followed the same 3 files structure based on Google's recommended pattern. 1. Component file. This wraps the logic into a reusable KFP component. It defines the Docker image, uses specific install dependencies, accepts input and returns the outputs, and return a small Python code in a controlled environment. 2. Pipeline file based on DAG definition. This connects components into a logical sequence. Each step depends on a previous step. Output from one step is passed to the rest. 3. Compile file. Vertex AI doesn't read YAML for version 2 pipelines. We compile the pipeline into a JSON spec file. This file becomes the single artifact representing the entire MLOps workflow. Before running any pipeline inside Vertex AI, we needed a storage location for all pipeline artifacts. Vertex AI pipeline always writes logs, intermediate files, and metadata into a Google Cloud Storage bucket. Every pipeline run generates execution logs, metadata for each component, steps input and output, cached result, and system-generated JSON configs. If no bucket is specified, the pipeline cannot run. Why this matters for MLOps? Because it ensures full traceability, supports reproducibility, stores logs for debugging and monitoring, and enables versioning of pipeline runs all the time. To run a full MLOps pipelines on Google Cloud, Vertex AI must have proper permissions to access the required service. A pipeline interacts with cloud storage, BigQuery, Vertex AI pipeline, BigQuery ML, such as model training and forecast. Thus, we configure a dedicated service account that Vertex AI pipelines use to execute each component. This service account must be authorized to read and write the pipeline artifact bucket, read and write the BigQuery, such as model and queries, and executes the workflow in Vertex AI. If these permissions are missing, the pipeline will fail immediately. Once all individual tasks were validated, the full pipeline was created. This combines every component into one directed cyclic graph for depth. This is a real production pipeline that Vertex AI runs end-to-end. After defining the full pipeline, we compile it into a JSON spec file. Vertex AI pipelines only accept JSON for version 2. It is the artifact used to run a real automated pipeline inside GCP. Each component produces its own logs. Data loader logs, created train and test table successfully, model trainer logs, BigQuery ML model created successfully, and evaluation logs, printed AIC values. After the pipeline finished, logs validated that all business logic executed correctly. Outputs were written to an artifact bucket, and in a BigQuery console, the Arima Plus was successfully created. After the pipeline successfully executed inside Vertex AI and the Arima model was trained in BigQuery ML, the next phase was API development, converting the trained model into a production-ready service. BigQuery ML stores the model internally, but end user cannot run SQL queries. Applications require a REST API. Inputs must be validated and outputs must be returned in a clean JSON form. So the goal was to transfer raw ML model to a real scalable API service. The file contains the core computation layer. The design keeps the API thin and pushes all business logic into a reusable module. To demonstrate the model visually and interactively, a small UI was built with a data picker choose the forecast start date, a horizon selector, a button to trigger API calls, and a clean results table. This provides a simple and user-friendly interface for running forecasts without writing any SQL code. Before containerizing the API and deploying it to Cloud Run, I needed to ensure the environment was fully reproducible. This is where the requirement text file comes to play. In machine learning projects, especially for full MLOps workflow, reproducibility is critical. Creating a precise and clean requirement text is a foundational prerequisite before moving into Dockerization and production deployment. After preparing the requirement file, the next major step was containerize the API. This is a key part for MLOps lifecycle because the Cloud Run only deploys applications that run inside a Docker container. A Dockerfile defines exactly how the application should be built, which Python version to use, which system libraries are needed, which Python packages must be installed, how to copy and run the Fast API app, and which port the service will listen on. Once the Dockerfile was ready, the next critical step was to build a container image locally and confirm that the entire API behaved exactly as expected. This is the standard best practice in MLOps. We always validate it locally before pushing anything to the cloud. I use Docker to create a full local image of Fast API service. After the image was built, I ran it locally to validate it functionally end-to-end local testing. After the image was built, I ran it locally to validate functionally to an end-to-end process. By validating everything locally first, I guaranteed that deployment to Cloud Run would be smooth and free of surprises. After validating the Docker image locally, the next step was to prepare Google Cloud to store and manage my production container images. For this, I used Artifact Registry, which is Google Cloud's secure and fully managed container registry. Before deploying to Cloud Run, the Docker image must be stored in a central secure versioned repository. Artifact Registry provides version of the images, high-speed integration with Cloud Run, and regional storage for lower latency and cost. This step is essential in a real MLOps pipeline because it establishes the secure, consistent image management before moving to production deployment. After the Docker image was successfully pushed to Artifact Registry, the final stage of deployment was to turn it into a fully managed, production-grade web service using Cloud Run. Cloud Run is the execution environment that hosts the Fast API application and exposes it securely over HTTPS. At this point in the workflow, everything was ready for deployment. The Fast API was fully implemented, the Dockerfile was tested and validated locally, and the container image was stored and versioned in Artifact Registry. Once deployed, Cloud Run provided a public HTTPS URL for the Fast API service, automatic SSL and TLS certificate, scalable pay-per-use infrastructure, and system health checks. At this point, the entire system was live and accessible. The same forecasting logic that originated in BigQuery ML and was wrapped into a clean Python inferences layer was now available as a fully managed API endpoint. This project brought together every stage of a modern MLOps workflow, from building clean business logic, designing reusable KFP pipelines, orchestrating model training in Vertex AI, and managing artifacts in cloud storage, all the ways to the package the model into the Dockerized Fast API service and deploying to Cloud Run. The result is complete end-to-end machine learning pipeline running seamlessly on Google Cloud, demonstrating both technical depth and real-world engineering practices. I hope you enjoyed this video and thanks for watching.